Okay, hello, everyone, and welcome to Knowledge Algebra. Today we'll be discussing uh, chapter 2, section 2.1, which talks about graphs. It talks about functions and graphs. So let's begin. So the definition of a graph. The definition of a relation. We shall begin our discussion on graphs by looking at what is a relation, and then from a relation we can move on to establish an understanding of a relation. Then we can move on to um, define what a function is. So a relation is a set of ordered pairs. Any set of ordered pairs is known as a relation. And so any set of ordered pairs, for example, we can have 1, 2, what is this? 3, 4, and 5, 6. So this is an ordered pair. So we call this a relation. The first components of this ordered pairs are known as the domain of the relation. And the second components are known as the range of the relation. So you can have an example that says, so let's look at an example. Find the domain and range of the relation. And the relation is this set of ordered pairs 0, 1, 8, 7, 1, 2, 1, 2, 2, 2, 2, 5, and 3, 3, 3. So the domain will be the first values of the relation. So the domain will be these points 0, 1, 2, and 3. The first point should be the domain, and the range will be the second points of the relation. So 1, 8, 7. Right here. 1, 8, 7. 2, 1, 2. 3, 2, 5. And 2, 3, 8. So these are the first points. So this should be the domain and the range of the relation. Okay, so now let's move on to define a function. So a function is a correspondence from the first set called the domain to the second set called the range, such that each element in the domain corresponds to exactly one element in the range. Or you can say a function is a relation such that each element, so now that we know what the relation is, you can say a function is a relation it's a relation where each element in the domain corresponds to exactly one element in the range. So a function is a kind of relation where each element in the domain maps on exactly to one element in the range. So for example, we can say determine whether the following is a function or not. So let's see this example. Let's use this example to determine whether the given relation is a function or not. Determine whether the relation is a function. And the relation is 1, 2, 3, 4, 6, 5, and 8, 5. All right, so if we look at this, each element in the domain, um, each element in the domain maps onto exactly one element in the range. So let me write the domain as one. The first element are the domain 1, 3, 6, 8. And the range is 2, 4, 6, 2, 4, 5, and 5. So if we look at this, each element in the domain maps onto exactly one element in the range. So this is why that is why we say this is a function, because we don't have a case where you have one element in the domain mapping onto multiple elements in the range, or there's a one-to-one correspondence. All right, so let's look at another example. Let's determine whether this is this relation is a function or not. So you are giving 1, 3, 2, 5, 1, 6, and 5, 8. So the domain is the first element of 1, 2, 1, and 5. And the range is 3, 5, 6, and 8. All right, so if we look at this, we have 1 maps onto 3, 2 maps onto 5, And we have 1 mapping onto 6 again. And 5 maps onto 8. All right, so because we have 1 which maps onto both 3 and 6, this is not a function. This relation is not a function. Because you have the same elements in the domain that is mapping onto more than 1 element in the range. So that disqualifies this relation from being a function. Okay, so we can also look at functions as equations. If an equation is solved for the y value, a more than one value of the y can be obtained for a given x, then the equation does not define as a function. So to determine whether a function is an equation, if we solve for y, for any function, y is equal to f of x. If we solve for the value of y, then we get more than one value for the same x value, then this function is not, this function is not this equation is not a function. So let's use an example to explain. So let's use this example. So example to be example 3. Determine whether the equation defines y as a function of x. Determine whether the equation determine whether the equation defines y as a function of x. All right, so we have, for example, x squared plus y squared is equal to 1. So if we solve for 1, if we solve for y, we have y squared is equal to 1 minus x squared. So if we take square root on both sides, then we'll have y is equal to plus or minus square root of 1 minus x squared. Okay, so because we have 2 values of y for the same value of x. So for one value of x, for one value of this x, we are getting 2 values. So this means y is equal to positive square root of 1 minus x squared, and y is equal to negative square root of 1 minus x squared. So for one x value, we have 2 values of y. We have 2 values for y. So that means this is not a function. So if we have the same, for the same x value, if we have 1, for the same x value, if we have more than 1 value for the y, then that means the equation is not a function. Let's look at another similar example, b. So if b, if we have y is equal to square root of x plus 32. Okay, so for this is a function because for every for one x value, you only have one value for the y. So this is a function. This is a function. All right, so let's look at function notation. Um, so if f of x represents the value of a function at the number x, um, so for function notation, we represent function as if we see f of x, what this means is for a value is a function f for the value or for a number x. So this represents the value of the function at the number x. So for the number x, the value is the value of the function at the number x is what f of x represents. Let's look at this example here. If f of x if f of x is equal to x squared minus 2x plus 7, evaluates f of minus 5. So f of minus 5 means let's replace the x with 5 and simplify. Okay, this equals to, in place of x represented by negative 5, so negative 5 squared minus 2 times negative 5 plus 7. And so this is equal to negative 5 squared is 25, negative 2 plus negative 2 times negative 5 is positive 10, we have plus 7. So this is equal to 42. So f of negative 5 equals to 42. Graphs of functions. Graphs of functions. Let's discuss the graphs of functions. All right, so the graph of a function is the graph of its ordered pairs. Let's use an example to explain. The graph of a Taylor function is the graph of its ordered pairs. So, for example, we can graph a function by picking x values and we evaluate to find the corresponding y values. And once we find the corresponding y values, we'll have a set of ordered points. And from these ordered points, we can plot them. So let's use this example. It says graph the functions f of x is equal to 2x and v of x equals to 2x minus a in the same rectangular coordinate system. All right. So to graph the first function, f of x is equal to negative f of x is equal to 2x. What we do is we pick a set of x values and we find the corresponding y values. So we pick a set of x values. So x is negative 2, negative 1, 0, 1, and 2. So for these x values, we find the corresponding y values, and y is equal to f of x. So for each of these x values, we find the corresponding y value. So if x is equal to negative 2, then y is equal to 2 times negative 2, which gives us negative 4. If x is equal to negative 1, we have y is 2 times negative 1, which is negative 2. And if x is equal to 0, we have 2 times 0, which equals to 0. And if x is equal to 1, we have 2 times 1, which is equal to, we have 2 times 1, which is equal to 2. And if x is equal to 2, then we have 2 times 2, which is equal to 4. So we have this set of ordered pairs, minus 2, minus 4, minus 1, minus 2, 0, 0, 1, 2, and 2, 4 for x. So we can use these ordered pairs to plot the function. Let's also look at get the ordered pairs for g of x is equal to 2x minus 3. So for g of x equals to 2x minus 3, we have our x values again. X values we can pick from negative 2 to positive 2, so negative 2, negative 1, 0, 1, 2. And our g of x, so our y is equal to 2x minus 3. So if x is negative 2, y is 2 times, negative 2 minus 3, and that is negative 7. If y is negative 1, we have 2 times negative 1 minus 3. So that gives us negative 5. If y is 0, if x is 0, we have 2 times 0 minus 3, which gives us negative 3. If x is 1, we have 2 times 1 minus 3, which gives us negative 1. And if x is 2, we have 2 times 2 minus 3, which gives us 1. All right, so we have a set of ordered pairs for x and y for the two functions. So we can now plot these points on the graph as such. Let's try to do that. This is this is 2, 4, 6, 8. This is negative 2, negative 2, negative 4, negative 6, negative 8. This is 2, this 4. This is negative 2, negative 4. This is negative 6. And this is negative 8. And this is 2. This is 4. This is 6. And this is 8. Okay, so let's plot the let's plot f of x first. So f of x, we have negative 2, negative 4. So the first set of points is negative 2, negative 4. So that is about here. The next one is negative 1, negative 2. So negative 1, x negative 1, y negative 2 will be about here. The next one is 0, 0. So 0, 0 is here. The next one is 1 and 2. So positive 1 and 2 will be about this point. The next one, the last one, is 3 and 4. So x is 3 and y is 4. It's about this point. So we see that we have a straight line through the origin. So we have a straight line through the origin. So this is the graph of f of x is equal to 3x. Now let's graph. Let's look at the graph of g of x is equal to 2x minus 3. So for that, the first pair of points are -2, -7. So -2, -7 is about here. The next one is -1, -5. -1, -5 is about here. The next one is 0 and -3. 0 and -3 is about here. The next one is 1 and -1. So 1, x is 1, y is -1, is about here. And the last one is 2 and +1. So x is 2 and +1 is about this point here. So the graph of g of x is also another straight line. This is also the graph of g of x is equal to 2x minus 3. All right, so this is how we graph. This is how we draw graphs on the number line. We in a rectangular coordinate system. We pick values for the x, and we pick from the x values we find the corresponding y values. Then we are able to get a set of ordered pairs. Then from those set of ordered pairs, we can graph the function in the rectangular coordinate system. So let's look at the vertical line test of how we test whether a function, how we test for functions using the vertical line test. So the vertical line test, what it says is if any vertical line intersects a graph in more than one point, then the graph does not define y as a function of x. So it basically means if we draw a vertical line through a function and the vertical line intersects with a graph more than once, then that graph is not a function. So let's use an example to explain. So this is example 6. So it says use the vertical line test. To identify graphs in which y is the function. It's a function of x. All right. So the first graph is this, we have a graph that looks like this. So determine whether this is a graph or not. You can draw a vertical line. So you can draw a vertical line through this. So this is how the graph looks. Determine whether this is a graph or not. You can draw a vertical line through this. And if the vertical line intersects once, then it is a function. So let's draw a vertical line through this. Because a vertical line through this intersects once, this is a function. The vertical line intersects once, intersects the function once. So this is the function. All right, so let's look at another one. You have a graph that looks like this circle here. You have a graph that looks like this circle here. Let's draw a straight line through it. So if you draw a straight line through it, you can see that a straight line intersects this more than once. So this is not a function. A straight line, a vertical line intersects the equation more than once. So this is not a function. All right, so let's look at another one. We have a graph that looks like this. If we draw vertical lines through this, you can see that the vertical line on either side intersects one. So this is a function. So that's how we determine whether an equation is a function or not. So let's also look at how we can determine how we can identify the intercepts of a function from a graph. Let's look at how we can determine the intercepts of a function from a graph. And so let's look at this example on this slide here. So let me share my screen again. Okay. So assuming we have a graph, we are given a graph such as this, and we are asked to identify the intercepts from the graph. So what we do, for example, we are told that this is a function f of x, and that we are to find f of 5. So to find f of 5, what we do is we look at the x-axis and we trace 5 and look at, and what we do is we look at where 5 is on the x-axis, and where 5 goes up to meet the function, we check the corresponding value on the y-axis. So we can see that if you trace 5 from the horizontal axis, it meets the function at the place where on the y-axis the function equals to 400. So that means f of 5 is equal to 400. And in the same way, if we are given f of x is equal to 100, and we are asked to find the corresponding value on the x-axis, we look at where 100 is on the x-axis, and from that point, we determine the corresponding x value. So if you look at 100, so the lowest mark point here is 200, and so 100 is in between 0 to 200. So if we trace horizontally, if we trace the value of 100 to meet the graph, we can see that at where y is equal to 100, the corresponding x value would be 9. When y is equal to 100, if we trace a horizontal line to the graph on the x-axis, we will determine that the value of the x value of the function is also at 9. Okay. Also, let's look at how to identify the domain and range of a function from a graph. So looking at the domain and range of a value of a function from a graph. So on a graph, it says, so let's look at this example 8. It says, use the graph of the function to identify its domain and its range. So the domain of the function is on the interval in which the function lies on the x-axis. So if you look at this function, it lies on the x-axis. If you look at the blue rectangle, you can see that this function on the x-axis, it exists between -2 and +1. The area that the blue rectangle covers on the x-axis is between -2 to +1. So that means the domain of this function is -2 and is between -2 and +1. But when we talk about the range, it's also the interval on the y-axis in which this function lies. So we look at the y-axis. So if we look at the red rectangle, you can see that on the y-axis, this function exists from 0 to 3. On the y-axis, you can see that this function goes from 0 to 3. So that is how we determine the domain. We look at on the x-axis the interval in which this function lies. On the x-axis, we can see that it goes from -2 to +1. Include close parentheses because those points are included. So we have a square parenthesis, and on the y-axis, it lies on from 0 to +3. So this is how we determine the domain and range for a function on a graph. We can also look at another example. So in this example, we can determine the domain and range. So the domain again, on the x-axis, this function lies between +1 and -2. But remember, on the -2, the point is not shaded. So that means it is an open interval. It is an open interval at the -2 point. So in the domain, this lies between +1 and -2, but -2 is open. So x is really greater than -2, but less than or equal to +1. And on the y-axis too, we can determine that the function lies on the y-axis. It lies between -1 and +2. On the y-axis, it goes from -1, which is the lowest point of the function, and it goes to +2. So that is how we can determine the domain and range of the function. So on the x-axis, it goes from +1 to -2, but -2 is open because the point is not shaded. And on the y-axis, it goes from -1 to +2, all included. So this is how we determine the domain and range of a function from the graph. So let's also look at how to identify the intercepts of a function from a graph. Let's look at how to identify the intercepts of a function from a graph. So let's look at another example. Okay, so in this example, it says identify the x and y intercepts for the graph of f of x. So the x-intercept is where the function intercepts with the x-axis. So you can see that the red points, that is where the function intersects with the x-axis. So the x-intercepts are -3, -1, and +2. Those are the red points, the point at which the function intersects with the x-axis. So -3, -1, and +2. And the y-axis, the y-intercept is the point on the y-axis on which the function intersects with the graph. So on the y-axis, we can see that -6, the blue point, -6 is where the graph intersects with the y-axis. So that's the y-intercept. So the y-intercept is -6. The x-intercepts are -3, -1, and 2. All right. Let's look at another example where we evaluate a function if we are given certain x values. So for example, let's look at some other example here. All right, so for example, if we are given for example, let's call this example 4b. For example, if we are given f of x is equal to 6x minus 6, and we are asked to find a f of x plus 2 and b f of negative x. So if we are asked to find this, so f of x plus 2 implies wherever x is, we replace it with x plus 2. So that will be equal to 6 times, in place of x, we replace it with x plus 2 and minus 6. So this equals to 6 times x, 6x, 6 times 2, 12 minus 6. So this gives us 6x plus 6. And f of negative x means wherever x is, we replace it with negative x. So that will be equal to 6 times negative x minus 6. So that's equal to negative 6x minus 6. All right, and let's look at some other examples. We will call this, I'll call this example 4C. It says let f of x be equal to x squared minus x plus 6 and g of x and g of x and g of x is equal to negative 2x minus 4. And we have to find g of 5. And f of g of 5. So g of 5 means wherever in the function g, we replace x with 5. So it's equal to negative 2 times 5 minus 4. So negative 2 times 5 is negative 10 minus 4. So that gives us negative 10 minus 4, gives us negative 14. And now we have to find f of g of 5. We've already found g of 5, which is equal to negative 14. So this implies we can find f of g of 5, which is negative 14. So this equals to, in the function f, we replace x with negative 14. So this equals to negative 14 squared minus negative 14 plus 6. So, and if we evaluate this, this will give us 216. Let's look at one last application problem. So it says, this will be our example 9. Okay, so example 9 says, suppose the average yearly salary suppose the average yearly salary of an individual whose final degree is a master's. It's a master's is 43,000 less than twice that of an individual's final degree is a bachelor's. and combine two people with each of those educational attainments. Those educational attainments and 160,000. Find the average of an individual with each of these final degrees. Find the average income, the average yearly salary. With each of these final degrees. All right, so we are told that we have two people, one with a bachelor's degree, one with a master's degree, their combined income. So if you just say, let M represent the income of the master's, the income of the master's degree holder, and let B represent the yearly salary of a bachelor's degree holder. The yearly salary of a bachelor's degree holder. And so if we do that, we are told that their combined income is $116. So M plus B is equal to 116,000. And we are also told that the master's degree's income is 43,000 less than double of the bachelor's degree. So master's degree's income is 2 times the bachelor's degree's income and 43,000 less. All right, so from here we have two equations that we can solve to obtain the income for both. So we already know from equation 1 that M is equal to TB. We already know from equation 2 that M is equal to M is equal to 2B minus 43,000. So we can substitute M in equation 1. So then equation 1 now becomes, in place of M, we have 2B minus 43,000. And this plus B is equal to 116,000. All right, so B, 2B plus B is 3B. So 3B minus 43,000 is equal to 116,000. And so if we add 43,000 on both sides, then we'll have 3B is equal to 116,000 plus 43,000, which gives us 159,000. So we have 3B is equal to 159,000. If we divide both sides by 3, we have B is equal to 53,000. So the yearly salary for a bachelor's degree holder is $53,000. And we already said M is equal to 2B minus 43,000. So that means M is equal to 2 times B, which is 53,000 minus 43,000. So this is 2 times 53,000 is 106,000 minus 43,000. So a master's degree, so that's yearly salary is equal to 63,000. All right, so this is our last example, and so we will end here, and we will continue with section 2.2 in the next video. Bye-bye.